Good evening, friends. It's about to be at 7 p.m. and today's class is half an hour early, so students will be joining in soon. Co-host can at least help them to join in. And madam, you can please continue. Okay. Today's class will be up to 8:30, 7 to 8:30. So 1.5 hours class will continue as per the convenience of madam. You can close as per your convenience. There is no issue, madam. Okay.
Yeah, okay.
Okay, madam. Please continue.
Right. So in the last class we had looked at different things for simple pendulum. Primarily we had looked at how to find the equation of motion and then how to find the time period from the equation of motion for the simple pendulum. So just in case, the equation of motion that I'm talking about is basically this. F we can write as ma, and then for a we can write d2x by dt square. So then d2x by dt square is equal to minus gx upon l is essentially the equation of motion. So between relation between acceleration and displacement essentially. So that we had seen, and we had also looked at this particular formula, which is the time period for simple pendulum, which is again, just to reiterate, this will be 2 pi into root of L upon G. And we had also seen one example, and then I had mentioned in the last class that we'll not take any examples from we will not take examples in that class, but we'll start the next class with some examples, because this topic, the topic of simple pendulum, is essentially one of the important topics. Just like spring, it is equivalent to spring, and many questions, I just noticed that in CET, for example, in the same question paper, there were multiple questions from the same topics, and one of the topics was simple pendulum. So if you do this one topic, then you can easily score one or two questions like that. So it is important topic, and then I thought I should give more time to questions on this topic. So before we move to questions, I will quickly say two three things in here first. So first thing is about how to find the energies in the simple pendulum thing, because there were also many questions based on finding energies in a simple pendulum motion. So right, so we'll just talk briefly about energies. And you'll also see direct application of the formula that we work out now in the questions in few minutes. So basically, let me just draw the pendulum again. And this is like a more like a conceptual thing that you can apply to multiple places in multiple examples. So I'll just cover it here instead of separately doing it in the questions. So this is essentially your simple pendulum motion, and this is length of pendulum L, and this is some angle theta, right? And let's just say this is some position A, which is not extreme position. We can just assume that it is some middle position A, between the mean and the extreme. Um, Between mean and extreme. And this is the position B, which is equal to the mean position, right? Now in the simple SHM with the spring, what we had seen is that velocity, first of all, is maximum when the particle is at its mean position. So this is the point. This point is where V is equal to V max, and kinetic energy is equal to maximum kinetic energy, and that still holds in the case of simple pendulum. So V at point B is just going to be equal to V at mean, and that is just going to be equal to V max. So in this motion as well, the same thing holds, that at the mean position you will get the maximum velocity. And the other thing, which was that at the extreme position the potential energy is maximum, that case also holds here. So at VA, so velocity here is going to be zero, but the potential energy is going to be the maximum. So VA is going to be, which is equal to V at extreme position, is going to be just zero. Whereas now let's see the potential energy. So this is equivalent to kinetic energy, right? Essentially. So we are talking about kinetic energy there. Kinetic energy will be maximum at the mean position, and kinetic energy will be equal to zero at the extreme position. And now similarly look at the P, which is potential energy. So potential energy at the mean position is going to be zero, and the potential sorry and the potential energy at extreme position is going to be maximum energy essentially. Now we have not formally derived a formula for what is the maximum energy in this system, in a simple pendulum system. Just like how we had done in the spring system, it was half k a square, so that was the maximum energy or the total energy in the system. So like that, we have not derived a similar formula here, but there is a nice little trick that you can use to find out energies at different positions, even in the simple pendulum case. So what is that trick is essentially, see, we are always, we will always know the kinetic energy of the particles, right? Because kinetic energy is just going to be equal to half mv square. And we can always know v at some position, or that might be also given in the exam, in the question. So we can almost always find out the kinetic energy of particle at different positions if the v is given. It is very straightforward. But now how to find the potential energy is the question. So the like a neat trick for that is just to assume that because at the mean position, at this mean position, all the energy, the total energy, whatever energy that we have not calculated, that total energy is always going to be equal to the kinetic energy of that particle, because all the energy at mean position comes from kinetic energy of particle. So essentially what that means is half m v max square, or half mvb square, because b we have taken at the as the mean point, is going to be equal to total energy of the particle. So this is something that will come handy for you when you're trying to solve some problems which are talking about the energy in simple pendulum system. So this is total energy. Okay, so how this helps, we'll just see now. So what we'll do is we'll apply the conservation of energy. We will so basically in a simple pendulum system as well, the energy is always conserved. Energy stays the same. So what that means is this is now your total energy, half mv max square, and that energy will stay conserved regardless of at what point your particle is at. So now imagine we need to find out the energy. We need to find out the let's say potential energy at this point. Now for this point A, we know that its kinetic energy is just going to be half m v a square, right? And then there will also be a potential energy component. Now we can play a neat little trick, and we can just assume that this is your ground. ठीक है? So it is not very physical, but it works. So we can just assume that your pendulum is at like the lowest point of the pendulum. It's exactly very close to your ground, and then we can say कि ground के यहाँ पे आके potential energy zero हो जाएगी, because the so you know the potential energy, gravitational potential energy is essentially PE gravitational is just mgh, right? That is something you know already कि अगर this is your ground and your body is like your box is somewhere here at on a table, then the potential energy of this box is just going to be mg into this height h, right? This is something you have probably learned already. So we are going to use the same formula here, and we are going to say कि इधर for the mean position the h is just zero, because the bob is almost touching the ground, right? And because of that the potential energy is zero. And similarly we can use the same trick to say कि when the particle is at a position, let's just say its height is some value h. Okay, and given that h, the potential energy of such a particle is just going to be mgh. So the total energy of the particle at point A, at any random point A in its journey, is just going to be half mva square plus mgh. Now the trick is here to find out what is h, because you will say ki h bhi to we don't know na, h how, like h is also not given to us. So how are you going to find the h? So let me just erase this. So for the edge, we are going to consider this triangle. Okay. So let's just, this is the pivot point, and this is your L, and we are going to consider this triangle. This is the position A, and this is the total length. This is where the bob is essentially. So this total length is L. This total length is L. Okay. And now we need to find out this distance. This is H. So this distance H, let's say this small distance is just some value A, this side of the triangle, right? And then we can find out H is equal to L minus A. So this entire L, how to highlight this? Yeah. So this entire L minus this A is just going to be H, right? The value of height. And now L value we have, but again, A we don't have. But A we can find out by considering this right angle triangle, and let's say this is some theta. And you can see that A side is essentially is going to be, I mean, if you take cos theta, for example, then the cos theta is just going to be adjacent side A into hypotenuse, this hypotenuse, right? This is your hypotenuse. So that is L. And now we can find out A in terms of theta and L, which are the known quantities, as A is equal to L cos theta. And then H is just going to be L minus L into cos theta. This is just going to be L into 1 minus cos theta. Now we know L will be given in the question. We know theta will also be given in the question. And from this value, we can find the H number. And now the total energy at some random point A is just going to be half mVA square plus mgl into 1 minus cos theta. So this is something important. I mean, this is not given in your textbook, but this is something that could come handy in some of the problems revolving around the energies of in a simple pendulum system, right? And now there is like a very also another neat little trick which you can do is just equate these two values. Sorry, these two things, because this is also total energy. This is total energy at some point B, and this value is total energy at some point A, and the total energy of the system is always going to stay conserved, right? So you can always say that this value, the half mva square plus mgl 1 minus cos theta, is equal to half mv max square. Similarly, now if you see this point, which is now, let's see, this is some point C, and the C point is the extreme point. Okay, so B point is the mean point, A is some random point, and C is the extreme point of the pendulum, right? And for the C pendulum point, what we are going to essentially have is the kinetic energy, as I mentioned, ki at the extreme point, the kinetic energy of the particle will become zero, and all energy it has will become the potential energy, right? And so the total energy at point C is just going to be, I mean, this term, the VC square at extreme position, that is just going to be zero. And then for uh, the theta will essentially become zero, because it is at the extreme position, right? And then because of no theta will become the maximum value it can become, because this is the extreme position, and theta will just become theta max, because that is the maximum angular coverage that the pendulum has. And because the theta becomes maximum value, cos theta will become its maximum value, and the maximum value of theta, cos theta, is 1, right? And so this just no wait uh there that should not happen. No, sorry. Yeah, maximum value in the sense, okay. Yeah, my bad. Theta becomes maximum because it's a cos function, not a sine function. So, like sine 90 is 0, but cos 90 is 1. So that was the confusion. When the theta becomes, for example, say 90, it's an extreme case. But when the theta becomes 90, the value of cos theta is going to be 0, not 1. That was a mistake. And then 1 minus 0 is just going to be 1, and the entire energy the particle has is just going to be mgl. Okay, so this is a simple trick that you can play, and we'll see how it works out in the in the question paper. You can maybe write down this formula and maybe also this formula. These are like some of the these are the two important formulae that are not there in the book. And then there is like another here is they have given one activity which is not exactly activity because they have given wait where is the they have given the um, they have essentially given the explanation of why your theta needs to be zero. Sorry, theta needs to be very small, and how small it could be for the given formula of time period to be valid. So they have given what are the errors if you take say theta is equal to 20 degrees, theta is equal to 45 degrees, like that, and theta is equal to 90 degrees. Then what are the errors in the actual time periods with respect to the time period that is given by this formula. And the point that they are trying to make is essentially that for this formula to be valid and give an accurate representation of the actual time period, you need to have theta values which are lower than a particular value. And that is just the point of that. And you can go like read through this. And then the another thing they have given is the conical, like a comparison between a conical pendulum and a simple pendulum. So this is probably not really important because I did not see because I don't think this is there in the JEE or CET question like syllabus, and I didn't also see many questions at the end of this chapter based on the conical pendulum thing. So you can just read through it. They have also not given much of explanation, so they probably don't expect you to like derive these things and all. But conical pendulum is essentially so for simple pendulum we said that the simple pendulum has to like the bob has to move in one plane, right? The plane of the paper. It should not go in the third dimension. For the conical pendulum is basically when the bob is allowed to move in third dimension, and it essentially covers a or like a tracks a circle instead of this is an arc, right? This simple pendulum is tracking an arc. Instead of that, conical pendulum just basically tracks a horizontal circle. um, so, so you can imagine matlab ki you will give a theta to a pendulum and then it will track this kind of motion, like a circular motion. And in that case they have given the time period of there's no derivation of this provided, so you can also probably just remember this. And if you see some question, it will most likely be based on time period or angular velocity concept. So you can just remember that this is the time period 2 pi into root of L cos theta. So cos theta term is new here, and like in addition with the simple pendulum this thing. And with that I think we can go to the like the question part, and then we'll come to the angular SHM in a while after we solve the questions. So I have added like a formula sheet here again. There was like some part of the formula sheet that was erased in the last time, so I have added it again. Huh. So from here I have added some of the things like same formula. You can just look through it. It's a collection of formulae. And yeah, we'll start from here. So these are like sort of arranged in the increasing order of difficulty. So this first question is quite simple. So they have given a simple pendulum of length L, has a brass bob attached to its lower end. The period of this simple pendulum is T. Now a steel bob of the same size. So the keyword here is same size. The size does not change, having density X times that of the brass. Same size but the density is increased. It replaces the brass bob. So the mass was first of brass, and then they change it with the bob of steel mass which has density x times that of the brass. Now the next thing is the length is so changed that the period becomes 2t. Now the length is, let's say, L dash, and L dash has a period of 2t. Now what is this L dash? What is this new length? Now there are two things to consider here in the question, which is firstly the density of the blob is changing, but the size stays the same. And the second thing is the length of the blob is changing. Now like the relation between density and mass is essentially that density is equal to mass upon volume, right? So the volume is it is staying the same here, and there's a direct correspondence. Matlab ki density, if the density is increasing, then the mass will also increase because the volume, because the size is same. Now if you remember, I had mentioned in the last class that for the simple pendulum, I mean, you can also take a look at the formula, which essentially says that you don't see a term of mass here, you don't see a term of density here. What that essentially means is that time period of a simple pendulum, it does not depend on the mass of the blob, is also does not depend on the density of the blob. The only thing that it depends on is the length, right? Length of the pendulum. And last time I had mentioned that this length is considered or calculated from the point of pivot to the center of the blob. नाउ अगर क्वेश्चन में ऐसा दिया होता कि बिकॉज ऑफ दिस डेंसिटी चेंज द मास stays the same but only the density is changing. What that means is the mass stays, this is now constant, and the density has changed. What that will imply is the volume will also change, and volume change का मतलब क्या होगा कि the radius of this blob has changed, and if the radius of the blob changes, then the length of the blob will change, and that will affect the time period. But because they have given that the size of the blob is not changing at all, so because of that, radius will also not change, and because of that, length of the pendulum will also not change. So this is an important, like they might try to trick you in this case because they have given key density x time change hogi, or options maybe you see options which have that x value. So this is like a trick thing कि इट माइट मेक यू बिलीव कि एक्स पे डिपेंड होगा जो आंसर आएगा वो, बट दैट इज नॉट द केस बिकॉज द टाइम पीरियड ऑफ द सिंपल पेंडुलम डज नॉट डिपेंड ऑन mass or density of the mass attached to it. Given that, now the next thing that they have done is they have changed the length such that the time period becomes 2t. This is something we can calculate, so that's what we are going to calculate. um, so let's just say the time period is 2t, and for that we can write the equation key L dash upon G, and we can just take ratio for t, and this is just going to be L upon G, the original length. And then t will cancel, and 2 pi will cancel, and G will also cancel, and what you will see is 2 is just going to be equal to L dash into L. And that just means ki we'll take square, and then that will just mean ki L dash upon L is equal to 4, which will mean ki L dash is equal to 4L. So this is the only answer. Like you'll see that answer does not depend on the value of x, value of the density of the blob. So this is going to be the answer, and that is like indeed the answer. This was one of the CET questions, I think. This is also, the next question is also CET question. Next question is, let L1 be the length of simple pendulum. If its length changes to L2 to increase the time period by 20%. So let's just say when the pendulum की length is L, let's just say कि time period होगा T तब. And then when the pendulum की length is L2, let's say time period is some L2, and they have given key L2 is 20% higher than T2 is 20% higher than T. So we can just calculate the value of T2. So T2 is equal to T plus T into 20 by 100, and this is going to be T plus 0.2T, and this is just going to be 1.2T, right? And then we'll write the similar kind of ratio again. And if you noticed here in this question, you will just see कि T2 upon T1 का जो relation है, it is just L2 upon L1, right? Because this was our T dash, so T dash upon T is just equal to root of L dash upon L. So we can just take the same thing in the below question. And just we'll write T2 upon T1 is equal to root of L2 upon L1. So T2 here is 1.2T, and T1 is just T, and root of L2 upon L1. So this is just going to be 1.2, and then we'll take square of both sides. So this will be L2 upon L1 is equal to 1.44, 12, like square of 12 is 144. And so L2 is just going to be 1.44 into L1. So the ratio of L2 upon L1 they have asked, and the ratio of L2 upon L1 is just 1.44. So this is the answer. That is indeed correct. And this is, I think, a NEET question, NEET 2023 or 2024. Um, this is another, like a different type of question. So simple pendulum has a time period of T in air. Okay. Its time period when it's completely immersed in a liquid of density 1/8 the density of the material of blob. Uh, so I've taken this question because here also we are talking about the density of the material of the blob, and in the first question also we talked about the same thing. But I'm taking this question to show that they are not essentially the same questions, and this is like a question where the density of blob will actually matter. We'll see how. And they have asked the density, sorry, time period in the liquid. ओके नाउ सिचुएशन क्या है यहाँ पे कि हमारे पास ब्लॉब है विच इज लाइक अगेन अटैच टू समथिंग एंड फर्स्ट वी लुक एट द दिस थिंग in air, the time period in air, and then we calculate T air, um, and then we take a glass or something uh, filled with some type of liquid, and then we just fully immerse this blob into this liquid, and then we try to see what is the time period in such a case, and the density of liquid. So the density of liquid they have given is 1/8 of the density of the material of blob. So this is equal to 1/8 of density of blob. Now we know key formula to find this is 2 pi into root of L upon G. तो यहाँ पे essentially G कहाँ से आ रहा है? G आ रहा है based on the kind of force that is acting on the blob, right? When we derive this formula, the G comes from mg essentially, and this is the force that is acting on the blob. And now we'll have to again check whether this force acting on the blob inside the liquid, does it stay the same or not. And easily we can say ki the force will not stay the same, because यहाँ पे you are not only looking at the gravitational force, but you are also looking at something called a buoyant force, which is acted by the liquid on the blob. So this is your blob. I'm not drawing liquid, but let's just assume there is liquid inside this, and we know that there is a force acting downwards, which is mg, but there's also this force acting upwards, which is the buoyant force acted by the liquid, which is opposing this mg force, right? It is holding the ball upwards, um, and so the total force, the force effective, let's call it. So we need to find the effective force and then substitute that effective force here, and not just take the g. So the force, like effective force, is going to be mg, which is essentially the gravitational force, minus, because this force is acting in the upper direction, in the opposite direction of mg, minus the buoyant force. And buoyant force, I'm not sure if you have seen this formula or not before, but this F buoyant is, it can be given as volume of the blob. So the amount of liquid that the blob will displace, volume of the blob, into the density of the liquid essentially. So the rho L and then G. Okay, so this is the F buoyancy formula. And then we can substitute that here in the F buoyant thing. But we can also substitute M for, because from this formula we can, or I can just write again. Uh, 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 hmm. So rho is just M upon V, right? And so we can just write M as rho of ball into V of ball. Okay? And then G. And then we can substitute this formula, which is rho of liquid into V of ball. The volume will stay the same, because the force is acting on the same volume, and the amount of volume that is getting displaced of the liquid is also volume of the blob. So VB will stay the same, and then G. And so we can just do this as VB into G into rho of blob minus rho of liquid. And rho of liquid is 1/8 of rho of ball. So we'll just write this as rho B minus 1/8 rho B, which is going to be equal to 7/8 rho B into PBG. And now we want to substitute here force upon the um, like we want to substitute an equivalent of G here, right? Acceleration upon displacement essentially. So we just need to divide this by mass to get the equivalent of G, and the mass here is rho B into VB, because that is what we had substituted here, rho B VB. And so this is just going to be divided by rho B VB, and then the acceleration divided by displacement is just going to be equal to 7/8 G. Okay, this is like a subtle point what we have done here. So maybe write it down, or yeah, note it down somewhere how we did this, because there were like many questions like this, like of this similar kind in previous question papers that I saw. And then time period now from here is just going to be 2 pi root of L into A upon X, and this is just going to be 2 pi root of L. A of X is 7/8 G. Okay, and this is just equal to 2 pi L upon G into root of 7/8. So this is the T, this is the original T, and no, sorry, 8/7. Like this 8/7. And this is the original T that they have given in the question. And so, so the T2 is just going to be equivalent to 8/7 into T. So this is the final answer. Uh, um, yeah, root of 8/70. So yeah. Uh, right. Yeah. This is basically the example of the formula that we saw in the like first few minutes of the class. So this is basically a blob of a pendulum bob has a speed of 3 meter per second at its lowest position. So at lowest position, meaning this is the V max. So this implies V max is equal to 3 meter per second. The pendulum is 50 centimeters long. So the length is 50 centimeters, which is equal to 0.5 meter. The speed of bob when the length makes an angle of 60 degree with the vertical. G also they've given. G is just 10 meter per second square. Um, okay, and then they have asked um, the speed of bob when the length makes an angle of 60 degrees. So this is the vertical and this is the 60-degree angle. And this is where your blob is. This is the lowest position. And they have asked the speed at this position A. So VA is equal to what? And and they have given the V max. So we can just use you like remember recall the formula that we saw in that PDF, which is key. Firstly, V max, like the kinetic energy, or we can just say total energy is just equal to half m V max square, which is in this case half mv 3 meter per second square, and then the l- like the energy at uh, point A is just equal to so they have not given whether A point is like at extreme or not. They have just said ki some position where the length of this thing is making angle of 60 degree. So we can just assume that it is a random position. It is neither a mean position nor an extreme position. Um, and given that logic, we can just write this as half mva square plus mg into L 1 minus cos theta. So this is the energy at point A, right? And we have been asked to find out the speed of the bob. So we need to find out this VA, right? Now this total energy and this total energy is just going to be same. And as I had mentioned earlier, you can just equate these two things whenever you need, right? So what we are going to just say is key total energy is always conserved. So this is the fundamental principle that we are invoking. Key total energy of the blob is conserved, which implies that the half mv max square can be equated to half mva square plus mgl 1 minus cos theta. Okay, so this is like an important thing. This is a important trick. And then we can just start putting in values. So we can firstly m cancel. If you notice in the question, they have not given the value of the mass of the blob. Okay, and if you try to say calculate these values one by one, instead of like writing this equation all together, you can also find the values of individual constituents and then take the values and equate those values, right? That also you can do, but they have not given the mass value. So this is like you shouldn't get confused कि अरे mass value तो दिया ही नहीं है, तो how can I find these individual components? You should keep that in mind कि अगर आपने equate कर दिया सारे needed terms को, then your mass value is just getting cancelled. So you don't need the mass value. So you shouldn't panic in such case. You should just write the entire equation in terms of variables and then try to see कि कौन से चीजें cancel हो रही है. Um, so this is like a nice tip. And then we can just write this as half mv max square is equal to half mv a square plus gl into 1 minus cos theta is 60. So cos 60 is half, and 1 minus half is just going to be half. And then half also you can cancel. You don't need to calculate that. And now we need this va square. So we're just going to write va square is equal to v max square minus gl, and v max is 3 square 9 minus g is 10 meter per second and l is given to be 0.5 meters, and this is just going to be 5. So 9 minus 5 is 4 meter square plus centimeter per centimeter to the power 4. This is va square, and so va is just 2 meter per second. Uh, so the answer will be 2, just 2. And yeah, this is correct. So like now, like you can probably appreciate that formula more now. Ki how neatly everything just fell into place, and although m was also not given, the m got cancelled, so you didn't need m like that. So like keep this formula in your mind, even though it's not given in the book. And this is like the final example that we'll look before moving to the class. And this is a very nice example. It utilizes multiple concepts at one at single time. This is also slightly more involved. So like pay attention about like how we solve this. So the given information is this is a JEE paper 2023 or something, or 2024. Um, like mains, okay, not even advanced, but this is a nice question. Like it's a good difficulty level. So the question is a simple pendulum with length 100 meter. So we're just going to write this in form of meter centimeter for now. We'll see why. And then a bob of mass 250 grams. So mass is given this time 250 gram. Executing SHM of amplitude 10 centimeter. So um, for the simple pendulum, we have not yet encountered the concept of amplitude. We only know L, which is the maximum length of the pendulum, but amplitude we have not yet defined. So we'll also talk about that concept. Uh, Amplitude is 10 centimeter. The maximum tension in the string is found to be x upon 40 and the value of x is. So the question is to find out T max is equal to what? And I will just draw the figure again of a simple pendulum, because this is like a conceptual thing also, not just numerical. Let's just note of that. Yeah. So this is theta, and this is a simple pendulum that we had taken a look at. Um, and then if you remember how we had derived that formula, we had taken this T, and we had taken this mg and then made it into different components. This was mg cos theta and this was mg sin theta, and then we had equated this sin theta with the like the restoring force, and then that restoring force was minus mg sin theta, and from there we had found out the T value. Okay, so this is the tension that we are talking about, key the tension in the string, and then they have asked the maximum value of the tension. So first concept here that will come here is the maximum tension is where in this motion essentially. Is it here? Is it here? Is it here? Is it here? Is it where is the maximum tension in the string? So the straightforward answer to that is maximum tension in the string will be at the mean position, because as you can imagine here the blob is directly facing downwards, and the entire mg, like both components of mg are facing downwards. Here you can say ki tension is compensated by only cos component of mg, but here because the theta is just in straight line, theta is just 0, so entire contribution of mg is in the vertical direction, which means it is in the direction of tension. And so because of that the maximum tension in the string will be at um, so the T max will happen at mean position. So this is something you can also like keep in mind. Um, and then we will again use the formula that we had derived in the other page. So that formula was essentially, or like the another concept will be here, key maximum energy in this system is also at the mean position. So T max will happen at the mean position, and now we have to find out what is the formula, like a analytical form of T max. And for that, what we will see is firstly we'll get a contribution from mg because it is directly going in the like negative direction, and there will also be a contribution from a centripetal force, because this blob is essentially performing a circular motion, and to hold that like when the blob is moving in a circular motion, you know that centripetal force also acts in the blob, and that blob, like that centripetal force, is also always in the negative, like outwards direction. So it is always in the external direction, which is also the same direction of mg here. So like the two forces are coming, one is coming because of gravitational energy, gravitational force, and the second is coming because the particle is moving in an arc which is a part of circle, and everything that is in circle sees this centripetal force, and the value of this force you might have already learned in the class is mv square upon r. R is the distance between the pivot point and the mass, which is in this case is L. So we'll just write mv square upon L. So this is the form of T max. Okay. First, this thing is coming because of gravity, and this thing is coming because of circular motion. And now mg we can easily find. They have given the mass, and g we can take equivalent to 10 meter per second square. Now we need to find out this mv square. L also has been given here. The quantity that has not been given here is v square. M is given, L is given, v square has, like velocity is not been given. Particularly, we need the velocity at this position, at the position essentially where we are looking to, like where we are working at. We need the velocity at the mean position, but that has not been given. What has been given, like then extra information. So we will use L, we will use M, we will use G. but the remaining information is amplitude. Now we have to make use of this amplitude to find out velocity. Okay, now we'll see how we can do that. So amplitude in such kind of motion, um, just like linear motion, you can say ki amplitude here is, if the other side of motion is like this, then amplitude will essentially be this point and this point. So let's say this is the extreme position and this is the extreme position. Then the projection of these two extreme positions is the minus a and a. So this is the amplitude that we are talking about, and this quantity essentially. And now if we take the same quantity here the block, and look at this triangle, then this is the theta and this value is sine theta, right? So the amplitude is essentially going to be amplitude in simple pendulum is just going to be a is equal to L sine theta, because if you see this position is, let's say, that is amplitude. So sine theta is just a upon L, and then a is just L sine theta. So this is another important concept कि amplitude कैसे define करते हैं इस motion में, so that is just L sine theta. And now we have this theta thing here, and now we will again look at this same formula. This formula, we will just take that formula below, and let me just write that down again, mv max square, and this time we need this max square. Okay, v max square, that is the value that we require, because this is that is what will go here, this mv square. Oh no, I forgot to write m. So mv max square is equal to, now if you remember, instead of taking this whole formula, we will now look at, instead of looking at some random position ka energy, we will look at the energy at the extreme position. And if you remember, the energy at extreme position, I had talked in the another PDF, that energy will just be equal to the entire potential energy, right? And um, so we can just write that as mg L 1 minus cos theta. ठीक है? So this will be the, and we'll just say कि entire energy of that block at extreme position is just going to be potential energy. So this is at extreme position, and this is at mean position. So mean position पे entire energy will be kinetic energy, and extreme position पे entire energy will be potential energy. So these are the two things that we are equating. So okay, this is a subtle thing. So like pay attention maybe. Um, so and the total energy is always going to be conserved. So that is the fundamental concept that we are using here. And using that, we have not been again given cos theta, but now we know the value of sine theta. And we can cleverly use the value of sine theta in this equation to solve it again. And then we'll just continue with that idea. So half mv square is just going to be mgl 1 minus, I think all of you know this trigonometric thing, which is just 1 minus sine square theta, right? Because sine square theta plus cos square theta is 1. And if we take it on the other side, we'll just get that cos theta is equal to root of 1 minus sine square theta. So we'll just plug that here, 1 minus sine square theta. And yeah, and then this will be that, but we need here mv square upon L. So we can just figure that formula out, and then we can just plug this whole information here. So we'll just take mv m square by L is just going to be, this 2 will go on the other side, 2 mg, and this L will just get cancelled, so L won't be there, and 1 minus root of 1 minus sine square theta. So this is now the value of mv square upon L that we can directly substitute here. So we will take that formula here, and we'll just say tension, like the maximum value of tension is just going to be mg plus 2 mg into 1 minus root of 1 minus sine square theta. And then try to always simplify the analytical form as much as possible before plugging in the value, so that you'll avoid making like repetitive calculations, and it will save your time. It is easier to work with letters than like actually calculating. So this will be equal to mg1 plus 2 into 1 minus root of 1 minus sine square theta. And now we can start plugging in these values. So mg, m they have given is 250 gram, and that we can just directly convert to kilogram, which will be 0.25 into g is 10 into 1 plus this, like if you open this bracket, this will just be 2. So 1 plus 2 is just 3, and then 2, this bracket will go inside, and that will be 2 into root of 1 minus sine theta square. So sine theta we have figured out is um, sine theta is equal to a upon l, and a is given to be 10 centimeter and L is given to be 100 centimeter. So now you see why we kept this thing, because the 10 centimeter upon 100 centimeter will just happen, and then the centimeter will go. So you don't need to like remove those things. So this is just 1 upon 100, and this is just going to be 1 upon 10. And then we need the square here. So 1 upon 100. So this will just be 2.5 into 3 minus 2 into 1 minus 1 upon 100. And you can solve this 1 minus 1 upon 100 like with a calculator as well. But if you see here, this is a numerical type of example, so you need to have an integer value for like answer, because you won't get like decimal points answers here. So you can either solve this using calculator and then approximate maybe to find out the integration sorry, integer values. But if not, then you can also use this like a identity sort of, if you can remember this maybe, and then that identity will be 1 root of 1 minus x square is just going to be equal to 1 minus x square upon 2, and this holds when x is very less than 1. So in this case, our this thing is 1 minus 1 upon 100, or like 1 minus 1 upon 10 square, like 1 minus this thing, right? 10 square. And then that just means that x is equal to 1 upon 10. And 1 upon 10, we can just say that, so this x square has to be, yeah. And then 1 upon 100, we can just say that it is very less than 1. And approximately, we can say that this identity is satisfied, like that condition is satisfied. And so we can just write this as 1 minus 1 upon x square upon 2, which just means x square is 1 upon 100 into 2, which is just 1 minus 200. So this is like just to keep the things in integer. This is a trick that we can use, or the identity that we can use. And then just taking this thing again, T max is just going to be equal to 2.5 into 3 minus 2 into 1 minus 1 upon 200, and then this is just going to be equal to 2.5 into 3, and this will be 2 into 2 is like just 1. 3 minus 2 is just 1, and then plus 1 upon 100. And then if you solve this, the answer will just come out to be like 101 or something. I mean, I have already gathered 2 pages of this thing, so I'll just, yeah. You can simplify this, but these were like the tricks that we use mainly, like things that are worth remembering for also other questions. So first will be that T max happens at the mean position. Then the second concept was what is the value of T max. Um, I'll just write this neatly again. So the value of T max will be mg plus mv square upon L. And actually, in general, like a general value of T at any point, tension in the simple pendulum system is just going to be equal to mg cos theta, because that was the earlier term that we had looked at here. Ki this is the cos component that compensates for the tension essentially, and this the mv square upon L will stay the same because centripetal force in the entire motion of circle, it stays the same. So this is the formula for tension in any, like, a general position. And this was the second concept that we used. Then the third important concept was, a like an amplitude in simple pendulum motion is defined as A is equal to L sine theta. And then this is like like a normal thing, matlab a trigonometric kind of formula, uh, like an identity. It's not specific to simple pendulum, but it simplifies the things that the calculations that you're trying to do. So these are the four different kinds of things that we use in this example. So which is why I had said earlier that this is like a nice example. It utilizes multiple concepts, and it tests multiple concepts essentially, whether you know all these things or not. Okay. So like that's all for the questions. Say, I know it was like a slightly heavy thing, but it was necessary because there were like multiple types. So these are all types of questions, and if you do one type properly, if you know how to do this one type of question with any numbers, then um, the same question might get asked in a different form or with like different numbers of tension or amplitude or whatever. And then if you know how to solve that particular kind of question, you can solve multiple questions like this. So I just thought I'll take five different kinds of questions. And now we can come back to the remaining chapter. So it's like few pages are remaining. And these are, I think some of these concepts are not there for the JEE syllabus. That is something you guys should check. But for example, I didn't see any question on this magnet vibrating in uniform magnetic field or even angular SHM. And the next concept is damped oscillation. So I did not see questions related to this in recent exams. So you can probably check whether these things like these concepts are part of the syllabus or not. But regardless of that, you will see these questions in board exams. Uh, but they will be based on limited information. I feel they will not go in like much depth in these questions. So we can just look at them now. Um, so the so the important new chapter, like new topic, is angular SHM and the differential equation. So the first case they have taken is a rotating disk. Let's see. So what is happening here essentially is कि हमने एक disk लिया हुआ है. So disk can be like a coin of 1 rupee or something. And then we have made this one hole where you can attach this string, just like a normal pendulum. And then this disc is it has been hung from a support. And now instead of giving this disc like a simple pendulum motion, this is not the motion that we are giving in this case. What we are instead doing is we are rotating this disc like this. So we are just taking this disc and just moving it in clockwise or anti-clockwise direction. And you can also imagine like a swing. You might have played on swings when you were like small, and one person will like stand behind you, and then they'll try to rotate the swing, and then you are sitting on the swing, and once that other person stops like rotating the swing will move in the opposite direction. And like that was like a kind of fun thing that we used to do. But yeah, so it's the same concept essentially कि हम exactly same चीज कर रहे हैं यहाँ पे कि coin को लेके rotate कर रहे हैं in one direction, and because of this rotation there will be some potential energy, some restoring force that's getting stored in this string, and that restoring force will essentially give it the SHM kind of motion, because once you stop rotating, then that restoring force will kick in and it will start moving the coin in the opposite direction. Then once it moves towards the entire, like the all everything, it spends all the energy in one direction, it will stop at that point, and then it will again start moving in the opposite direction. You can exactly imagine the swing example. That is like a perfect example for this case. And now in such angular, like this is the angular SHM, because now you're like rotating, you're performing the motion of rotation, not just like oscillation. uh, and in the case of this rotational motion or like angular motion, the concept of force will be replaced by the concept of torque. So you might have already learned about torque in like अर्लियर क्लासेस, जहाँ पे आपने मोमेंट ऑफ इनर्शिया और लाइक एंगुलर मोशन ये सब से रिलेटेड जो टॉपिक है उसमें शायद आपने पढ़ा होगा कि टॉर्क क्या होता है एंड हाउ टू फाइंड टॉर्क एंड वगैरह वगैरह. So it is an equivalent of force in an angular motion. So force is when you're talking about linear motion and torque is when you're talking about angular motion. ठीक है. um, and I'm not sure if you've seen this formula or not, but if you're not, you should pay attention. कि टॉर्क कैलकुलेट करने का जैसे फोर्स, फॉर एग्जांपल फोर्स यू कैलकुलेट एज m into a. I can just make a table here instead. I can just say कि linear motion and angular motion, and we will see कि what is equivalent of what. So F का equivalent is torque. Similarly, mass का equivalent in angular motion is moment of inertia. Moment of inertia I. Then acceleration का equivalent is angular acceleration. Velocity का equivalent is angular velocity, and displacement का equivalent is angular displacement. So these are the equivalent things, right? So जैसे हम force को F is equal to ma लिखते हैं, वैसे ही m का equivalent is inertia, so moment of inertia, and a का equivalent is angular acceleration. So this is the formula for torque. Alpha, sorry. Yeah. सो जैसे आपको अगर याद है तो वी हैड फर्स्ट फाउंड आउट f इज इक्वल टू माइनस के एक्स इन द लीनियर SHM. So we will find the analogous formula for angular motion, which will be given in form of torque because force का equivalent is torque. And then we'll just write a minus something into x. X का equivalent is theta. This is not a like just drawing parallels is not very physical thing. I'll just say it upfront. It is not a physical explanation कि हम बस बोलेंगे कि linear motion में F है तो angular motion में torque है, linear motion में X है तो angular motion में theta है. This is not a very physical explanation, and I understand that, but it is easier to understand this way. Like going in this path, if we just draw these parallels, then it is also easier for you to understand. So otherwise there's a physical this thing which is also given in the book, so you can also go through that. So if we just draw parallels, then by that logic we will have F ka equivalent torque or X ka equivalent theta, and then we can just say some constant like like K. Here K was the force constant. We can just say C is the force constant for angular SHM. Okay, so this is the exact parallel that we can draw and it holds. It is still correct. And now we have this tau is equal to minus c theta, and then tau को हम लिख सकते हैं I alpha is equal to minus c theta, and then just like how we had written A is equal to d2x by dt square, similarly we can write alpha is equal to d2 theta upon dt square. ठीक है, सिमिलर केस कि हमने बस x को रिप्लेस किया थीटा से, and this is a correct expression. So we can substitute this alpha here here, and we can just write this equation as I into d2 theta upon dt square minus c theta, and this will just be equal to I d2 theta by dt square plus c theta is equal to 0, and this is the differential equation of angular SHM. differential equation of angular SHM. And you can draw parallels between um, this and the linear this thing, which was m d2x by dt square plus kx is equal to 0 for linear SHM. So you can see how I translates to m, sorry, m translates to I, and then x translates to theta, and then k translates to c, and x translates to theta again. It's the exact same form of the equation. It's just that now we have replaced the linear components of motion um, by angular components of motion. It's like, to explain it this way is it's easier to understand. And so this is the equation that is given in the book. So this is the differential equation of angular SHM. And then from here we can write alpha as minus c theta by I. So we can look at this equation. So from here we can write alpha is equal to minus c theta divided by I. Okay, this is another thing. And now we can also find the time period of this thing. And similarly the time period is again, we have this time period ka formula is 2 pi upon, remember this formula always, because this is a more fundamental formula ki, acceleration divided by displacement. And here again, for angular motion, the acceleration will be changed by angular acceleration, and displacement will be changed by angular displacement. So the formula for t in this case will just be 2 pi upon alpha divided by theta. And we saw ki alpha is this, so alpha divided by theta is just going to be minus c upon I. And we'll not take minus here, of course, because time period is like, we don't consider that negative. So we'll just take the scalar value, and this will be 2 pi upon c upon I. So this is just equal to k upon m that you had seen in the linear motion. And then there's no space here. So I can just write t is equal to 2 pi into root of I upon c. So this is the formula. You probably won't use it in like many places, but like it's probably a good formula to remember. Um, like if you can, matlab, it's not like a very important formula I feel, but just conceptually you can just remember the linear thing, and then you can just replace. Like you can just remember this table of linear and angular, and then you can just replace the elements. That is also like an easy way to remember this. And then we'll just look at the other concept, which is, okay, never mind, which is the magnet vibrating in uniform magnetic field. That is also, I'll just erase this. That case is also of angular SHM. Oh my god. Okay, wait, sorry. This just got moved. Okay. I will just let it be. Huh. So what I was saying is angular, angular SHM ka another example is magnet vibrating in a uniform magnetic field. So we'll just take second example, magnet SHM. So the premise or the physical reason of this is basically like a physical situation of this thing is, you have this uniform magnetic field which is in z direction in this diagram, and then you have kept a magnet here. So this is your magnet essentially, right? And this is the south pole, and this is the north pole, and this is the direction of your magnetic field. It is a uniform magnetic field, and you have kept the magnet at some angle theta. So this is some angle theta, let's say. Um, Now I'm not sure how much you guys are aware of uh, like a like a magnetic moment, and like what is the torque in this case, but it's probably not that important for the sake for the point that we are trying to make here. But like some formula to remember is just that when you have a magnet, which is, or like some physical reasoning to remember firstly, is that when you have a magnet in a magnetic moment, or like a, sorry, magnetic field, what it will try to do is it will just try to make it in the direction of the field. So if your field is in this direction, and um, if your magnet is lying in this position, which is at some angle theta, then this magnetic field is going to try to apply this torque, again a torque on your magnet, and make it aligned with the magnetic field. So if this is the magnetic field, then your equilibrium position for the magnet is going to be this vertical position, which is in the direction of the applied magnetic field. Okay. So while doing that, this B will apply some torque. Okay. And then that torque, again you can calculate like using I omega, but here we will not go in that way. We'll use this formula, the another formula of torque, which is R cross F. Okay. It's essentially the same thing. But here the force will come from the force that this magnetic field is applying, and then R will come from this thing, which is this distance, like this distance from the center of the magnet and the position at which the torque is being applied. Right. And this R is just going to be, if you say this is, I'll just draw a vertical line for a magnet. Let's say this is your magnet, and this is the angle that you're making, the magnet is making with the field lines. And then let's say you need to find out this motion, because this is the center of mass of the magnet, and this is where the force is acting. So we need to find out the distance between these 2 points, the perpendicular distance. And this perpendicular distance is just going to be, if the length of this, magnet is, let's say some like 2L or something, then this perpendicular distance is just going to be 2, sorry, L sine theta by trigonometry, because like this is the opposite side and this is the half of this whole length L, and this is just going to be L sine theta. And so we can just write this as L sine theta. You can probably not even pay attention to this derivation if you're not like familiar with these concepts in magnetism essentially. Like the derivation is probably not that important. You can just look at the like a formula that we finally get. And the force is going to come from the B, like the magnetic field that is acting on the um on a single charge. So there's no concept of, okay, I'll probably not even go in explaining this thing. We can just directly write down the formula, which is what they have done here. So this is the sine theta thing that is coming here, and then mu, that is given here, mu. So that mu is just magnetic moment, and that magnetic moment is defined in a different way for magnets than it is defined for electric charges, for example. So I'll not go into this way of deriving things because it will be like a weirdly non-physical. But we can just say that torque here that is being applied is just mu b sine theta. Now, sine theta term, you understood where it comes from, because we are taking this perpendicular distance. That is exactly the origin of that term. Mu is essentially the magnetic moment of this thing. So you can understand this mu b term as essentially the force that is being acted by magnetic field on the magnet, like the interaction of some magnetic property with the magnetic field, external magnetic field. And this is the mu b term, and the sine theta, it comes because of the perpendicular distance. And now we can just say ki, the torque that we are going to uh, like see, it comes from a smaller angular displacement, which is the similar principle that we looked at in the previous class. Ki in a simple pendulum, we always need the thetas to be small values. And so, considering that the sine theta, the small angle approximation, if you remember, is just approximately equal to theta for smaller theta angles. And then the tau can be just written as mu b theta. And this will, again, of course, be minus sign because it is a restoring force. So just to reiterate, the situation here is that this is your magnetic field that is in one line, and this is how your magnet is aligned. Now the magnetic field is trying to force this thing to be vertical, to be aligned with the direction of field. But if you try to keep moving this magnet in the opposite direction, that is, if you, it is the equivalent of like a stretching a spring essentially. So you're taking this magnet and moving in the opposite direction, and that is equivalent of stretching a spring. And what the force will try to do is it will try to take it back here, and then you're again putting a force in this direction, and then the restoring force is acting in this direction. So this is the mean point. So this is mean position, and like this the perpendicular position is the extreme position here. Just to draw an analogy. So that is because of that the the SHM motion is being generated, because you're trying to pull it this side, but the force, the magnetic force or the magnetic field is trying to align it in the vertical direction. So like that. Um, right. And the torque is now mu b theta, and we can just write the same equation again. Ki torque ko we will write I alpha is equal to minus b mu b theta, and then I d2 theta upon dt square is equal to minus mu b theta, and then this will just lead to um, this will just lead to I d2 theta upon dt square plus mu b theta is equal to 0. So this will be the differential equation of this motion. So if you see, we had earlier C here in the earlier example, and now we just have that C replaced by a specific form of C. So it is still the restoring constant, or like the force constant for angular motion, but now we have a specific form for that C, which is mu b. And then again, going by the same logic of acceleration divided by displacement. So this is the formula that we're looking at. Um, or yeah, this is the formula that we're looking at. And now going by the same logic of, there should be this thing, huh? Here there should be a divided by sign. I think here also they have missed it. So here also there should be a divided by sign. This is acceleration. Oh, acceleration, angular acceleration. Okay, per unit is there, so that's fine. um Maybe I'll just erase this. It has already has per unit. But anyway, huh. So going by the same thing, ki angular acceleration divided by angular displacement. So theta divided by, alpha divided by theta, and that is just going to be this mu b upon I term. And that is what we have put, ki mu b upon I, and then ulta side. So t is equal to 2 pi root of I upon mu b. It is very rare for you to get questions based on these formulae, but you can keep this in mind still. And you probably don't even, I mean, if you're not already been taught about these concepts in like magnetostatics or magnetodynamics, you probably don't even need to remember this like whole derivation, because like, I mean, it just will be like reciting the derivation, which is pointless. um, so they have given these two like a practice examples that you can take a look at. They are like fairly straightforward. They use the concepts of like moment of inertia. So I'm pretty sure you learned to find moment of inertia of different like rod or like sphere, like cylinder. All these things you have learned the formulae to find moment of inertia of. So they'll just play with these kinds of things. You find moment of inertia, or you find magnetic field, like that. um yeah, and then here you find the time period. So that's fine. And then now we'll come to the next, or like the last topic of this um chapter, which is damped oscillation. So damped oscillations is basically the most physical representation of oscillations in any case. So damping is basically, it opposes the motion of your block. So this is a simple pendulum and it's doing this motion. Damping will be, say, air resistance, for example, because our air, the like physical air, offers resistance to any kind of motion, right? So this will be always there. For example, in the case of spring wall system, this friction is damping. So any surface will have some friction coefficient, and that will eventually slow down the moving blob. So the blob will not go on forever in the physical case. So that is the damping, that is the case of damping in oscillators. And the oscillators which have this kind of opposing force inbuilt within them, they are called damped oscillations. So the formal definition is that if the amplitude of an oscillation is reduced by application of an external force. So here the external force is air resistance, or here the external force is friction, for example. This decreases the or reduces the amplitude of oscillations by external force. The oscillator and its motion are said to be damped. So eventually, this is like a thing that you have always observed. If you put a spring and a box system on some table or something, eventually, or like it'll perform, let's say, some 10 oscillations, it will go 10 times like this, and then it will eventually slow down, and dhire dhire, it will just, the motion will die down. So that is because of damping. Uh, okay, and now we'll look at the analytical form of the damping force. So the force of damping, it will be always proportional to velocity, and that to negative direction, because if your velocity is trying to pull this block outwards, the damping force will act in the opposite direction and will try to reduce or like the slow down the motion of this block. So it will always be proportional to negative side of velocity. And then we can just write Fd is equal to some constant b into velocity. So this is the damping constant, or something like, yeah, just like a proportionality constant basically. So this is damping, and this is the form factor of damping force. So we are looking at it here. And now let's say a spring is being damped, and we can write the equation of motion for such a spring. So equation of motion, or differential equation essentially. So we can write the differential equation as, original equation, if you remember, is m d2x by dt square plus kx is equal to 0, right? So basically f is equal to minus kx. But with damping, if you add damping to it, you will have the same equation as f is equal to minus bv minus kx. So both of these motions are opposing the velocity, or they are restricting the motion of the particle. So they are always in the negative direction of velocity and and displacement. So this is there, and then we can just write this in terms of, so v we can write as dx upon dt, and then this equation will just be m d2x by dt square plus b dx upon dt plus kx is equal to 0. So this is the d of damped motion. And they have also given the solution to this d. We'll not derive this solution, but you can, like, this is something that you can just remember very easily. So the solution for this thing is, the motion, or like the displacement x will be given as a, which is amplitude. So if you remember, the solution for this is just a x is equal to a cos theta, right? So this is the solution that we had seen, or like a cos omega t plus phi, something like that. So similarly, the solution here is just going to be a into e to the power minus bt upon 2 pi. So b is like this b, t is just time, and 2m, and then cos omega dash t plus phi. So if you see this cos omega t plus phi and cos omega dash t plus phi, these terms look similar, which means that the motion is still going to be a sinusoidal wave. So it will still be a sinusoidal thing. But now if you see, this is the amplitude essentially, right? This is the amplitude of your motion. And the amplitude is equal to A, which is the starting initial amplitude, into e to the power minus bt divided by 2m. Now you see this t. So t matlab time pe dependent hai amplitude. Earlier we did not have the dependence on time. So this a was just constant. And so the amplitude of this motion stayed constant throughout. But now in this case, in a damping case, you have a amplitude which is dependent on time. And how it is dependent on time? It is dependent as e ka power minus. So e ka power minus, the graph looks something like this. It does not touch this thing, it goes to infinity like this. And this is the exponential decay, right? And negative side ko dekha jaye to it will again be like this. So and then this is e to the power minus bt upon 2m, and then you still have the cos thing. So the cos variation will look like this. So you have an amplitude that is decaying like an exponential term, and then you have this additional varying term on time, which is varying like a cos theta. And so the resultant motion will look something like this. And this is, mind you, this x axis is displacement. It is the x values, and the x values are going to look like this sinusoidal wave, and they're going to follow these sinusoidal waves. So the plot of t versus x is just going to be like this, and eventually it will just damp down. The motion will stop like this. There will be no motion further. If you are asked the plot of amplitude versus time, then it will be this exponential function, because this is your amplitude. This value is just your amplitude, and that is the that is the graph for amplitude here. And now what about this omega t omega dash? So why we need that dash? So the dash is essentially like omega dash. So we will have a different omega value. It is still sinusoidal motion, but with a different omega now. And that omega here is just root of k upon m. So if you remember, this is your regular omega. So omega is equal to root of k upon m is the regular SHM omega. And now there will be an additional term, which is this minus b upon 2m square. So this is the omega dash, sorry. So this is the regular omega, root of k upon m is regular omega. And for damping, because of damping, the additional negative term, which is b upon minus b upon 2 ka square. So this just means that omega will be less than, omega dash is going to be less than omega. So what are the consequences of damping? First consequence is amplitude will be a function of time, and it will decay exponentially with time. Okay, so this is the plot of amplitude versus t. I'm just drawing the plot again and again because it is not given in the book. So this is the exponential this thing. It will not never meet. It will just go to infinity like this. So this is amplitude. And then the second important change will be that frequency of oscillations will be less in damping, like in damping case. So omega dash is equal to root of k upon m minus b upon 2m. And omega dash is less than omega. So these are the two important these things. Matlab, in an undamped case, if you looked at x, and in a damped case, undamped and damped. So the x plot in undamped case will look something like this. right? And in a damped case, so this is a time period, right? So this is going according to time. Frequency will decrease. Sorry, time. Frequency will decrease. Matlab time will increase. So for a damped case, you will have mm, something like this. Okay, not a great drawing, but yeah, you get the idea. Ki time, the difference in like the time at which this thing happens, it will increase because frequency is decreasing, and the amplitude will also go on decreasing. So these are the two main consequences of damping in a this thing, in a SHM, in any kind of SHM, linear, angular, anywhere. And this is a practical representation, matlab, because in physically all cases, in all cases, you will have something, some force that is opposing the motion. May it be like air resistance, it may be friction, or it may be air, like a water drag if you're moving underwater. So there'll be water drag. So things like that essentially. And like the only kind of questions that I could find based on the damping thing is basically about this frequency. So they had just asked what is the analytical form of frequency for a damping case, or some question had like a plot the graph between time and displacement, or time and amplitude. So things like that, this were asked, and we have already covered them. So this is something you can probably check if this portion is in your syllabus or not. And if it is in your syllabus, then there'll be very simple questions based on this thing. And I'll stop now because it's already 8:30, and it's like a heavy class today with all the examples and everything. So I'll stop here and we'll look at the free oscillations, force oscillations, and resonance. These three things, small concepts, we'll look tomorrow. Yeah.
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 Okay, madam.
Okay, madam.
Thank you so much.
Yeah.
We can stop here. And student, thank you very much for attending 1.5 hour session by madam. Tomorrow again the class is at again 7 p.m. So 7 to 8:30. Okay.
Yeah.
Bye. Good night. Good night, madam.